Triangular triumph. Unraveling the mystery of quantum spin liquids after 50 years. A collaborative research team has confirmed quantum spin liquid behavior in the material KYBSE2, validating a decades-old hypothesis. This breakthrough, significant for quantum computing and superconductor development, was achieved using advanced neutron scattering techniques and computational analysis. In 1973, physicist Phil Anderson hypothesized that the quantum spin liquid, or QSL, state existed on some triangular lattices, but he lacked the tools to delve deeper. 50 years later, a team led by researchers associated with the Quantum Science Center headquartered at the Department of Energy's Oak Ridge National Laboratory, ORNL, has confirmed the presence of QSL behavior in a new material with this structure, KYBSE2. QSLs, an unusual state of matter controlled by interactions among entangled, or intrinsically linked, magnetic atoms called spins, excel at stabilizing quantum mechanical activity in KYBSE2 and other delophocytes. These materials are prized for their layered triangular lattices and promising properties that could contribute to the construction of high-quality superconductors and quantum computing components. Collaborative research efforts. The paper, published on November 6 in Nature Physics, features researchers from ORNL, Lawrence Berkeley National Laboratory, Los Alamos National Laboratory, SLAC National Accelerator Laboratory, the University of Tennessee, Knoxville, the University of Missouri, the University of Minnesota, Stanford University, and the Rosario Physics Institute. Researchers have studied the triangular lattice of various materials in search of QSL behavior, said QSC member and lead author Alan Shai, a staff scientist at Los Alamos. One advantage of this one is that we can swap out atoms easily to modify the material's properties without altering its structure, and this makes it pretty ideal from a scientific perspective. Methodology and findings. Using a combination of theoretical, experimental, and computational techniques, the team observed multiple hallmarks of QSLs: quantum entanglement, exotic quasiparticles, and the right balance of exchange interactions, which control how a spin influences its neighbors. Although efforts to identify these features have historically been hindered by the limitations of physical experiments, modern neutron scattering instruments can produce accurate measurements of complex materials at the atomic level. By examining KYBSE2's spin dynamics with the cold neutron chopper spectrometer at ORNL Spallation Neutron Source, a DOE Office of Science user facility, and comparing the results to trusted theoretical models, the researchers found evidence that the material was close to the quantum critical point at which QSL characteristics thrive. They then analyzed its single-ion magnetic state with SNS's wide angular range chopper spectrometer.